Hey everyone, and welcome. Have you ever stared at a puzzle, one of those network or graph problems, and just thought, there's no way I can solve this just by looking at it? Well, today we're going to pull back the curtain on a really cool mathematical tool that lets you solve these tricky puzzles with just a little bit of simple algebra.
All right, let's just jump right in with a challenge. Picture a network. It's got 6 dots, or vertices, and 9 lines, or edges, connecting them. The question is, how many separate regions or faces does that create? Now, you could try to draw it, but seriously, trying to figure out every possible way to draw that, you'd be here all day and you still might not get it right.
Thankfully, there is a much better way, and it comes to us from this guy, Leonard Euler, and a formula that's so important it's right up there in the Math Hall of Fame with things like Pythagoras' theorem. It's this elegant, powerful shortcut that shows us a hidden truth about these kinds of shapes.
And here it is, v plus f minus e equals 2. I know, it looks incredibly simple and, well, it is. For any graph that follows a couple of simple rules, the number of vertices plus the number of faces minus the number of edges will always equal 2. It's like a law of nature for these drawings.
So let's quickly break down what these letters mean. Vertices, the V, are just the dots. Think of them like cities on a map. Edges, E, are the lines connecting those dots, kind of like roads between the cities. And faces, F, are the enclosed areas, like a farmer's fields. But, and this is the part that trips people up, you always have to count the huge, infinite area around the outside of the whole graph. That counts as one face. Don't forget that one.
Okay, so this formula is amazing, but it's not magic. It doesn't just work on any old scribble. The graph has to play by 2 very important rules for the formula to apply. Let's take a look at what they are. Rule number 1, the graph has to be connected. All this means is that it's all one single piece. You can start at any dot and travel along the lines to get to any other dot. You can't have any little stray points floating off on their own, completely disconnected from the rest. No islands.
And rule number 2, this one's a biggie, the graph has to be planar. What does that mean? It means you have to be able to draw the whole thing on a flat piece of paper without any of the lines crossing over each other. If the roads have to cross, then the formula is off the table. All right, now we know the formula, we know the components, and we know the rules. So we are totally ready to go back and crush that problem from the beginning. No more guessing, no more drawing. We're going to let the math do all the heavy lifting for us. So here it is again. We're assuming we have a graph that's both connected and planar. We know for a fact it has 6 vertices, so V is 6, and it has 9 edges, so E is 9. The piece of the puzzle we're hunting for is F, the number of faces.
First things first, we just write down our trusty formula. V plus F minus E equals 2. Now for the easy part, we just plug in what we know. We swap out V for the number 6, and we swap out E for the number 9. F is still our mystery guest, so we just leave it as F.
Okay, next up, let's just tidy this up a bit with some basic arithmetic. We can group the numbers together, so we've got F plus whatever 6 minus 9 is. Well, that's just -3. So our equation simplifies down to a much cleaner F minus 3 equals 2. See? We're getting so much closer.
And now for the final move. Just like in any algebra problem, we want to get our unknown variable all by itself on one side of the equal sign. To get f alone, we just need to add 3 to both sides. That leaves us with f equals 2 plus 3.
And there we have it. F equals 5. And that's not a guess, that's a mathematical certainty. Any connected planar graph that has 6 vertices and 9 edges must have exactly 5 faces. It's just the way it is. Pretty cool, right?
But hey, how can we be 100% sure we got it right? Well, the great thing about a beautiful formula like this is you can always check your work. Let's plug all 3 of our numbers back into the original formula and see if it holds up.
So let's do the final check. We put in 6 for V, our answer of 5 for F, and 9 for E. So, does 6 plus 5 minus 9 actually equal 2? Well, 6 plus 5 is 11, and 11 minus 9 is 2. Yep, it works. The numbers don't lie. Our solution is solid. I love how the source material puts this. It just says, spoiler strikes again. And it's so true. Once you know the formula, the puzzle loses its mystery. The answer is already there, locked inside the numbers. You could draw that graph a dozen different ways, but it would always have 5 faces.
So what's the big takeaway here? Well, first, Euler's formula is this super elegant tool, v plus f minus e equals 2. But you got to remember the ground rules. It only works if the graph is connected and planar. Its real superpower, though, is that it lets you find a missing piece of the puzzle with really basic algebra, telling you something fundamental about a network without ever picking up a pencil to draw it.
And that kind of makes you wonder, right? Euler's formula is just one example of a simple, beautiful rule that governs how complex shapes can be put together. It makes you think, what other simple formulas are out there just waiting for us to discover them that unlock the hidden patterns all around us?